Greetings and welcome to Distillate. For the previous classes, for the previous 5 lectures, we have discussed about the different basics involved in chemical engineering. The first video contained a few basic chemical engineering variables. In that video, we discussed about molality, mole fraction, mass fraction, and how to deal with questions involving these conditions. In the next video, we dealt with the ideal gas equation, which is PV is equal to nRT, where P is the pressure, V is the volume, N is the number of moles, R is the universal gas constant, and T is the temperature. R, depending on its unit, it has different values. And then we discussed about in the third lecture, we discussed about gas laws, where we dealt with Amagat's law, Dalton's law, and we discussed certain problems based on that. In that particular lecture, we discussed a very important relation for gas, which is mole percent is equal to volume percent is equal to partial pressure percent. All right. This relation we discussed, which was a very important relation. And then we solved certain problems related to that. In the fourth video, we discussed about two very important laws involved in liquid vapor equilibrium, right? We studied vapor liquid equilibrium and two very important laws involved in it. The first law is Raoult's law, which related partial pressure of a component to its mole fraction in the liquid phase. So this is how we had the Raoult's law. Pi is equal to P naught I xi, where P naught I is the vapor pressure of the component I. And then we discussed the second law, which was the Henry's law. So Henry's law states that Pi, again, it relates partial pressure to mole fraction in the liquid phase, and Pi is equal to Hi into Xi, where Hi is the Henry's constant. All right, and it has the same unit as that of partial pressure. All right, so this is what we discussed in the fourth video. And then in the fifth video, we discussed about stoichiometric calculations, where we discussed that if suppose we have this particular reaction, then we can derive a lot of information from this particular reaction. For example, we can understand what are the reactants, what are the products. Then we can understand how many moles of a particular reactant will react with how many moles of another reactant. And that would produce how many moles of different products, right? So if we have A moles of A, then that is equal to B moles of B. That is equal to C moles of C and D moles of D, right? That is what we discussed. And then accordingly, we can convert moles to mass and then do our calculations, right? So these were the few basic concepts that we dealt with. Please make sure that you're very clear with these basics before you start with the chemical engineering subjects. All right. So today we are going to start with the first and very important chemical engineering subject, which is known as chemical process calculations. Chemical process calculations forms the basis of almost all the subjects that you're going to study for chemical engineering. All right. In chemical process calculations, a very important concept is taught, which is known as material balance. Material balance. So in material balance, when you study about material balance, there are different steps involved while we are solving problems using material balance. So this particular concept is involved in almost all subjects that you will study, all subjects, whether it is mechanical operations, whether it is heat transfer, whether it is fluid mechanics, whether it is mass transfer, all the different subjects that you're going to study through your course, we'll be using material balance in almost every course somewhere or the other. So this particular concept is a very important concept. So please make sure that you're very clear with material balance. All right. So for the next few videos, we are going to deal with how to solve material balance problems, and we are going to discuss various problems so that you people are very clear with how to deal with concepts like these. All right. So the first thing that we are going to study for chemical process calculations is a block diagram. All right. So whenever we talk about a chemical industry, whenever we have a chemical industry, then we have a raw material which is used and then processed to form a finished product. All right. It is used and processed to form a finished product. For example, a very common chemical industry is the cement industry. All right. So in cement manufacturing, chemical industry plays a very important role, right? All the chemical principles that are taught, they are used in the cement manufacturing industry. So cement is basically produced using limestone. All right. Limestone is the raw material. Limestone is the raw material. And this limestone is used to form cement, which is clinker, which is also known as clinker. It is obtained as clinker. All right. So this raw material, it is processed in such a manner so that we get cement. All right. So it's very important for us to understand what are the different processings that are taking place on this particular raw material. How we use raw material, how we use limestone to get cement. How can that be possible? So for that, there are different processing units that are used, different methods that are used in order to convert this limestone into clinker, all right, or into cement. All right. And this is almost happening for every industry, that every chemical industry that is there. All right. So during the process of processing of this raw material, number of actions are done on this particular raw material. For example, we're breaking the raw material into smaller form because we have limestone. Let's say we have limestone. So limestone is a very big rock. It's a very big rock. So we cannot simply break it. We cannot simply transform it into a cement, right? We need to first break it into smaller parts. Then we can separate it into different constituents. We can even add chemicals to it in order to transform it into the desired product. Because whenever we are doing a particular, whenever we are working in a particular chemical industry, we need a combination of physical as well as chemical changes. All right, physical as well as chemical changes. We'll learn about all these things just in a few more slides. So let's go ahead. So this is how a basic chemical process takes place. All right, this is how a chemical process takes place. Okay, so first of all, we have raw materials, as I told you, and then at the end, we have the finished product. All right, we have the raw materials and we have the finished product. All right, this raw material needs to be transformed to form the finished product. All right, so in order to do that, we need physical treatment steps, chemical treatment steps, and then again, a few physical treatment steps. All right. So let's, for example, take a very simple reaction that you people might have studied in 12th standard. Nitrogen plus hydrogen gives you ammonia. All right. This is a very common reaction that is taught in 12th standard. So nitrogen plus hydrogen gives ammonia. So suppose we want to produce ammonia. All right. Suppose we want to produce ammonia. So in order to produce ammonia, so basically ammonia is our finished product. This is our finished product. All right. So in order to produce ammonia, we need nitrogen as well as hydrogen. All right. We need nitrogen as well as hydrogen. So how do we get nitrogen and hydrogen? So in order to get nitrogen, we require air, right? In order to get nitrogen, we require air. Similarly, in order to get hydrogen, we need some other ways. For example, we can get hydrogen by water gas shift reaction. It's a very common reaction. Water plus carbon monoxide gives you carbon dioxide plus hydrogen. This is a very important reaction. Again, this is taught in the 11th or 12th standard, right? So we can get hydrogen using this particular reaction. All right. Or there are many other reactions in which we get hydrogen, right? So these, whatever is the basic element through which you can get these reactants in this reaction. All right, this is our major reaction. Nitrogen plus 3 hydrogen gives 2NH3. So the different raw materials are basically those substances from which you can get these reactants. So what we have is, if I simplify everything, so we have raw materials that when processed, they give you the reactants. These reactants on transformation, this transformation is chemical transformation. So these reactants on transformation give you products. All right. And from these products, again, you might get 10 different products. All right. So from these products, you need to get the desired product. All right. You need to get the desired product, which is nothing but your finished product. All right. So from getting from raw materials to reactants, whatever happens in this particular part is your physical treatment. All right. Similarly, from product to desired product, whatever is happening in this part is the physical treatment step. All right. And between this reactants to products, whatever is happening over here, this is your chemical treatment. All right. This is your chemical treatment step. So there are these are very important. Physical treatment and chemical treatment. These two are very important. These two take place throughout. All right. In your chemical process. All right. So since we discussed just now that for a chemical process to take place, we need physical and chemical treatment steps. We need physical and chemical treatment steps. So we are going to classify whatever happens in a chemical industry, whatever units are there in a chemical industry, we are going to classify that into physical and chemical treatment. All right. So to classify them into physical and chemical treatments, we give them two different names: unit operations and unit processes. So unit operations is name given for physical treatment, and unit processes is the name given for chemical treatment. All right. Unit operations is the name given for physical treatment, and unit processes is the name given for chemical treatment. So when we talk about unit operations involve all the physical treatment steps that are involved in a chemical industry, right? Even if the composition of a mixture changes due to a treatment step, that too is a unit operation. All right. So we usually people, they get mistaken that if composition change takes place, that means it is a chemical change. No, it's not a chemical change, right? For example, if we have 20% salt solution, and from this 20% salt solution, I am making it to a 10% salt solution. So this is a physical treatment step, whatever has led to this. So this is basically a physical treatment. This is not a chemical treatment. Chemical treatment comes into picture only if you are making something else out of this, right? For example, here you have 20% salt. Let's see from this, if you're making 20% sugar, right? That's not possible. But if suppose you're making 20% salt to 20% sugar, right? So that is nothing but a chemical treatment. So when you're completely changing something, if you're changing the composition, then that is not a chemical treatment step. All right. So different unit operations in the chemical industry include distillation, filtration, sedimentation, mixing, drying, cooling, cooling or heating, which comes under heat transfer. Then material handling. Material handling, as in suppose if you have something in a drum, all right, something in tank, and you need to transfer it from here into another tank. All right, so you need to minimize the uh, minimize the amount of work that it involves to transfer it from here to here. So that basically comes under material handling. And then we have size reduction or size enlargement. Size reduction, in size reduction, we basically break something into smaller pieces. And in size enlargement, we accumulate smaller pieces together and we bind them to form a large piece. All right. So that comes under the unit operation. So as you can see in all these unit operations, distillation, filtration, sedimentation, mixing, drying, cooling or heating, material handling, size reduction, in all these things, whatever we are having, whatever originally, suppose before performing this unit operation, whatever we have, suppose if this is my unit, and this is some material that is being processed in this unit. So if I have something in this material, some material if I have, and I send it to this unit to get something else, so that something else is basically this material with a changed composition maybe, or with a different temperature, with a different pressure, with different volume, whatever. But it is not a different substance. Okay, it is not a different substance. If we are sending ethanol into this, then we'll get ethanol out. All right. If we are sending ethanol plus, let's say, water inside, then we are going to get ethanol and water out. Maybe they'll be separated, but we'll get ethanol, we'll get water, both of them separate, right? We are not going to send in ethanol and get methanol. That is a chemical process. That is a chemical treatment process. All right. So this, in all these distillation, filtration, sedimentation, mixing, drying, cooling, heating, material handling, size reduction, all these unit operations, these all are called as unit operations because whatever goes into the unit, it comes out as it is. All right, the same material comes out. There is no change in the material. It may be different in composition, it may be having some different properties, some different parameters, but it is going to be the same material. If you're sending A, you'll get A. If you're sending A plus B, you will get A and B. All right. Unit process is something that, suppose if you're sending, suppose this is your process happening over here. All right. And you are sending A, then you'll get B. All right. So this is what is called a unit process. So any treatment that brings a chemical transformation is categorized as a unit process. For example, we have nitration. All right. So if we consider nitration, so in nitration, let's say we have nitration of benzene. Right. So if we do that, then we have sent in benzene. We have got out nitrobenzene. Right. So this is a completely different product. All right. That is why this is a unit process. All right. That is why this is a unit process. All right. Similarly, there are others, for example, sulfonation, oxidation, reduction, polymerization, hydrolysis, chlorination, esterification or saponification, neutralization, and many more. All right. So all these reactions, all these chemical treatment steps, they come under unit processes. So unit operation is something that brings a physical change. All right. While a unit process is something that brings a chemical change. All right. Now we are going to represent a chemical process. So how to represent a chemical process? Suppose if I have my raw material, okay. Now I have done, let's say, step 1 on this raw material, then another step 2, let's say I'm doing a unit of performing a unit operation 1, then another unit operation 2, then another unit operation 3, then I'm getting my reactant from this A, then I'm performing a unit process number 4, then I'm getting B. All right, B is my product. And then from this, I'm again performing on this B, I'm performing another unit operation 5, another unit operation 6, another unit operation 7 to finally get my desired or my finished product. All right, so I'm doing all these steps, right? Now, how to represent, just like I have shown that I'm doing all these things. I'm doing step 1, step 2, step 3, step 4. So how to represent this? How to represent? Because we cannot simply write it down in a chemical process industry that, okay, first we are going to perform step number 1. From step number 1, we are going to get, suppose XYZ. Then we are going to put it in step number 2. From there, we'll get ABC. Then from this, we are going to put it into step number 3 and so on. We are not going to simply write down the description of this process, right? We need to simply represent it. You need to represent it so that it's easier for the workers over there. It's easier for everybody visiting that particular industry to understand that what's going on, what processes are taking place in the industry, right? So in order to get a clear picture of what is happening in the process, we need to diagrammatically represent it. All right. So there are 3 types of diagrams. These diagrams are also known as flow sheets. There are 3 types of flow sheets or flow diagrams that are used to represent a particular chemical process. All right. So the first diagram is known as a block diagram or simply a flow sheet. All right. The second diagram is known as a process flow sheet or a process flow diagram, PFD. And the third diagram is known as piping and instrumentation diagram or a PID. So when we talk about a block diagram, it gives us a basic idea of the chemical process. All right. So it contains blocks which represents the different units used in the process. For example, let's consider this process. Raw material, it's going into unit number 1, unit number 2, unit number 3. Then it gives us A, which goes into unit number 4 to give B, which goes into 5, 6, 7, and then finally get the finished product. So a block, to form a block diagram for this, we are going to take our raw material here and we are going to draw a block over here which represents process unit operation number 1. All right. Then from here, whatever comes out, it goes into 2, right? So we are going to contain another block that contains unit operation number 2. All right. And then we are going to do it so on. All right. So it contains blocks which represent different units used in the process, and each unit is connected to the other using arrows in order to show the order in which the processing is taking place. So the raw material is first going into 1, then from there it goes into 2, and from there it goes into 3, and so on. All right. So this is how we make a block diagram. Then we come to a process flow diagram. So when we talk about a process flow diagram, it gives us a more detailed view in comparison to the block diagram. All right. So it gives us stream information, that what is the composition, what is the, let's say I have raw material. From raw material, I'm getting this is the block diagram. So from raw material, I'm sending it into 1. So that gives me, let's say 25% A. Then that is going into unit operation number 2. That gives me 75% A. So all these informations are covered in a process flow diagram. All right. Moreover, it uses symbols to represent different units and equipments that are used. All right. It uses symbols so as to represent these different units. All right. So for example, if let's say we have to explain that we are using a sedimentation or we are using a thickener. Thickener is a unit that is used in chemical industries. So let's say if I want to represent a thickener being used, so I'm going to represent it in this manner. This is somehow that a thickener is represented, some a way in which thickener is used to be represented. All right. Similarly, let's say I want to represent a distillation column or a fractionation column. So something like this I'm going to use. And then for a batch distillation column, I'm going to use this, something like this. So, it uses symbols in order to represent the different equipments and units that are used. So a process flow diagram gives you a basic layout of the plant, right? How different things go on in the plant. All right, basic process layout. All right. And finally, we have piping and instrumentation diagram, which contains every information, every single information. For example, equipment details, its arrangement, its dimensions, its materials used for constructions, its rate or its capacity, its occupation time, its temperature, pressure. These are the temperature, pressure are also known as the operating conditions. All right, so it contains these. Then it contains the materials handled by that, heat duty, power, all these information. Apart from that, it contains pipe details, valves, ancillary fittings, pumps, instrumentation and control loops, services, symbols, layouts, everything. So it contains a complete detailed information of the industry. All right, of all the units that are used. So for example, let's take this process, production of ethane from ethanol. So we are now going to see how block diagrams look like. Block diagrams, process flow diagrams, PID. So before I go to this, we'll solve this as a problem. All right. So let me show you. This is basically a block diagram for ethane production. So over here you can see they have given different blocks. This is a block for reactor, and this is a block for distillation column. This is a block for condenser. This is a block for another reactor, right? So they have given us blocks, right? So that is why they are not giving any information about how this reactor looks like. They have no symbols for these. They have only given blocks to explain that, okay, something is going inside, something is coming out, right? Then a process flow diagram gives you a more detailed information. For example, over here, they have used symbol for reactor. Apart from that, they have shown that, okay, over here, we have used a pump and here we have a valve. Similarly, over here, we have a valve. Over here, we have a valve. Here we have a valve. And here we have a control valve. So this is basically a control loop. All right. Then over here, they have shown us the distillation column, the representation for a distillation column, for a condenser, then again for a reactor. So it contains somewhat more detailed information, and it also gives us certain, information about the layout of how it looks like. That of, okay, you're going to find reactor over here, you're going to find a distillation column over here, right? Something like that. Moreover, this is usually seen in a process flow diagram, that they don't write, just like for here in the block diagram, we have written whatever unit we are using just next to it or inside it, right? So for example, we have written reactor 1 over here, distillation column over here, then reactor 2 over here, something like that. But in a process flow diagram, we do not do that. All right, we simply mark it. For example, we have marked it as R100. We have marked it as R100. Similarly, V100, P100, V101, V102, CV100. CV is a control valve. All right. Then V103. So these informations, whatever we have over here, these are mentioned over here. So for example, R100 is a reactor, P100 is a pump, T100 is a distillation column, E100 is a condenser, P101 is again a pump over here. Then R101 is a reactor, and so on. All right. So all these informations are given separately, not on the diagram itself. All right. So these numbers, they are basically like indexes. All right, these are like indexes. So you have to see this number and find where this number is and see what equipment it actually is. All right, so this is how a process flow diagram looks like. And then a piping and instrumentation diagram is a very complicated diagram, very complicated diagram. It contains all informations about all different paths that are followed by a pipe, what are the different dimensions, what are the different walls, control loops, everything, whatever is used in a chemical industry, it is mentioned in quite detail. And over here as well, we use index numbers, you can see. And then these are further mentioned somewhere in order to give you an idea of what is taking place, right? So you can see this is such an easy diagram, a process flow diagram. This is such a complicated diagram, which is the piping and instrumentation diagram. It's a very important thing that you should know how this works. All right. So now let's go on to steps in making a block diagram. So when we have to form a block diagram. Block diagram is very important. Why am I stressing on block diagrams right now? Because when we will be dealing with material balance problems, then the first step to solve a material balance problem is to form a block diagram. All right. So you need a block diagram for solving any material balance problem. All right. So the first step is to identify the units that are involved. Next step is units involved are written in blocks. All right. So for example, if I have two units, I have one reactor and another I have, let's say, a distillation column. So I'm going to first of all identify that, okay, this is a reactor and distillation columns. And then we are going to write these units in blocks. All right. Then we are going to arrange these units in order as mentioned in the process description. All right. So whatever is the order in which, suppose if they have said that from the reactor it goes into the distillation column. So that means reactors first and then you have the distillation column. If they say it's the distillation column first, then from the distillation column it goes into the reactor. All right. Then we have to join the units using arrows. All right. We are going to join the units using arrows. And finally, we are going to mention information about input and output streams if it is given. All right. So since we have got these steps, let's go back to the production of ethane from ethanol problem. So let's now understand, read the process description, and let's do this as a problem, as an exercise, right? So ethanol is fed to continuous reactor with presence of acid sulfuric catalyzer to produce ethylene. All right. So this particular information, it actually is given for this reaction. All right. Then, so the first unit that we have identified is a reactor. Distillation process then will be applied to separate ethylene water mixture. So next unit that we have in next operation that we have identified is distillation. All right. Then ethylene as a top product is then condensate with condenser to perform liquid ethylene. So the third unit that we have identified as a condenser. And finally, hydrogenation of ethylene applies in another reactor, which is our fourth unit that we have observed. All right. It is applied in another reactor with the presence of nickel catalyzer to produce ethane as a final product. All right. So we have two reactors. So let's call them R1 and R2. All right. Then we have a distillation column. And finally, we have a condenser. All right. So these four units we have. Now let's try to understand that where is the feed coming, where is the product going out from, and how are we going to connect these. So again, we are going to go to order. All right. So ethanol is fed to a continuous reactor. So from here, you have ethanol. All right, from here you have ethanol with presence of acid sulfuric catalyzer to produce ethylene. Distillation process then will be applied to separate ethylene water mixture. So that means whatever is coming out of this is going into the distillation column. All right. So this would separate out ethylene water mixture. Ethylene as top product. So from top we have ethylene is then condensed with a condenser. All right. So this is going to go into the condenser. All right. And then to give you liquid ethylene. All right. Hydrogenation of ethylene applies in another reactor. So this is my ethylene, liquid ethylene. Now this is getting hydrogenated in another reactor. So let's have this, let's connect this to this reactor. And finally, to produce ethane as the final product. So from here we have ethane as the final. So let's actually draw the block diagram since you've understood what the process is. So let's now draw a block diagram very nicely. So we have first ethanol. Ethanol is fed to reactor number 1. This from this reactor we get ethylene. We get an ethylene water mixture. Now this is then fed to a distillation column. So this is my distillation column. The top product gives me ethylene, which means of course the bottom product gives me water. And this ethylene is sent into the condenser. All right. This ethylene is then sent into the condenser. And finally, I have made a symbol, but it's actually a unit. All right. Condenser. All right. And then finally, this from this condenser, it goes into the second reactor. So this is, and from here you get ethene. All right. So this is the basic block diagram, and that is something what they have given over here as well. All right, with slight more detail, but this is not really necessary. You must be well aware with different things. All right. So let's solve this problem. This is just an example, and just you have to form a block diagram. We don't have to solve anything. We don't have to do any calculations, nothing. We are just going to form the block diagram. So let's see. A mixture of benzene and toluene is fed to a distillation column. First unit, distillation column. So let's go here and let's make the first unit, distillation column. All right. And this is my distillation column. And here I have benzene and toluene. All right. At a rate of 100 kilomole per hour with mole fraction of benzene as 0.4. So let's mention this is 100 kilomole per hour, and the mole fraction of benzene, X mole fraction in the liquid phase, XB mole fraction of benzene in the liquid phase, 0.4. From the top of the distillation column, vapor is extracted at a rate of 60 kilomole per hour. So from here, we have vapor. We have vapor, which is extracted at 60 kilomole per hour. All right. And from this vapor is fed to a condenser, second unit. All right. It is fed to a condenser. This is my condenser. All right. Where it is cooled and the output is then fed to a separator. So here it is cooled, and then again we have another unit, which is the separator. Okay, so this is my separator. And from this separator, separator. Yeah. So this is my next unit, separator. So from this separator, we have said that 2 streams are taken out. So we are going to take out 2 streams out of the separator. stream 1, stream 2. First stream is sent back to the distillation column at the rate of 20 kilomole per hour, while the rest of it is taken out as product. So this first stream, we are going to send it back to a distillation column. This has come back to the distillation column, and the rate they have given it to be 20 kilomole per hour, right? They have given it to be 20 kilomole per hour. All right, and the rest of it is taken out as the product. So this is my product. All right, then from the bottom of the distillation column, that means they are talking about this part. This is the bottom of the distillation column. So from the bottom of the distillation column, further separating I'm so sorry. From the bottom of the distillation column, remaining mixture is taken out. The stream is fed to another distillation column. This is my second unit. This stream is fed to another distillation column. So I'm going to take another distillation column. So let's call it DC1, and this is going to be my distillation column number 2. Further separating the steam into top and bottom parts, the top stream comes out at the rate of 10 km per hour. So again, it separates it into top and bottom parts, and you have to find and the top stream comes out at 10 km per hour. All right, this is what our process was. So once again, let's see if we have taken all the units. Distillation column, condenser, separator, and another distillation column. So we have 4 units. So as you can see, we have drawn 4 units. Now material balance will tell you that suppose we have 100 kilomole per hour over here. So how to get the other values, 60, how to get this. We have 10 over here, how to get this. Then we have, I think, 20 over here, how to get this. So all these problems you'll be able to solve. We've just formed a block diagram. So using this block diagram, you will be able to solve various problems using material balance. So today's lecture was only about a block diagram. So you have hopefully understood how to form a block diagram. Now in the next class, we'll discuss about equations to use in material balance so that we can use this particular block diagram that we have formed in order to do our further calculations, and in order to calculate what is going to come out, how much of it is going to come out, and like that. All right.